Welcome back to The Explainer. I am absolutely thrilled to jump into today's topic because we're tackling one of the most foundational, yet honestly deeply misunderstood concepts in all of machine learning. Today, we are uncovering the truth of approximation. See, in AI, we almost never have the luxury of working with perfect, true data distributions. We only have our models, our approximations, and every single time we approximate, there is a cost. That cost is exactly what we are decoding today: Kullback-Leibler, or KL Divergence. You know that gradient we calculated in our last episode on vector Jacobian products? It's a powerful engine, for sure, but it's completely blind. We actually use KL Divergence to tell that gradient exactly which way to point. It acts as the operational compass for our models. But how does it actually do that? How does it measure the distance between what is real and what our model merely believes to be real? Okay, let's dive into this. Section 1, the tax on mistakes. To really get a visceral feel for what KL Divergence is doing, we need to step away from the abstract math for a second and step into the world of information theory. Imagine a classic telegraph key, the kind used by spies transmitting encrypted messages about enemy movements across a wire. Imagine you are that spy. In true venality, which we'll call P, the enemy attacks 50% of the time, and they retreat 50% of the time. That is the ground truth. But you have a flawed model in your head. Your model, which we'll call Q, mistakenly believes they're going to attack 90% of the time and retreat only 10% of the time. Because you deeply believe your model Q, you are going to optimize your transmission codebook based entirely on it. So you design extremely short, highly efficient signals for attack and terribly long, inefficient signals for retreat. Now, picture a visual cost meter attached directly to your telegraph. When the enemy retreats, which reality dictates will happen 50% of the time, you are forced to use that terribly long, inefficient retreat signal. Watch that cost meter rise. You are hemorrhaging transmission time. You are wasting bits. This right here is the fundamental rule of information theory. There is a tax on every mistake. Your flawed model literally costs you operational energy. And that brings us to the formal definition. KL divergence is simply the mathematical measurement of how much information is lost, literally how many bits are wasted when we use one probability distribution, our model Q, to approximate the true distribution P. It is the average number of bits you waste per transmission just because you use the wrong codebook. It brilliantly turns abstract probability errors into a tangible, measurable cost. Which brings us to Section 2, the asymmetry of divergence. Here's the twist that honestly trips up a lot of engineers, but getting this unlocks everything. What happens if we swap the distributions? What if reality P is 90% attack and your model Q is 50% attack? Well, you'd use a balanced codebook, but you'd be heavily penalized. This perfectly illustrates our next point. Being wrong about a frequent event is much, much worse than being wrong about a rare event. KL divergence heavily penalizes you when reality expects something to happen often, but your model completely failed to predict it. Because of this, the penalty depends entirely on whose perspective you are measuring from. KL divergence is asymmetric. We can prove this asymmetry definitively with some hard numbers. If we look at a simple three-state system and calculate the forward KL, weighing the penalty by the true distribution P, we get a total of 0.361 wasted bits. But if we flip it and calculate the reverse KL, weighing the penalty by the model's distribution Q, we get 0.471 bits. 0.361 does not equal 0.471. The distance from P to Q is not the same as the distance from Q to P. It violates standard Euclidean geometry entirely. Moving on to Section 3, forward versus reverse morph. Now, this mathematical asymmetry isn't just some trivia fact. It physically dictates the shape of modern AI. We really need to visualize exactly how these two different mathematical penalties forcefully warp and shape the geometry of our models during training. Imagine the true distribution P as two towering mountain peaks, a classic bimodal distribution. Your model Q, meanwhile, is a simple single morphing mound of clay. If we optimize using forward KL, the penalty for ignoring any real data is infinite. So watch the model stretch. It literally humps up, spreading itself super wide to desperately cover both mountain peaks of reality. We call this mean seeking. But if we optimize using reverse KL, the rules completely flip. The model is penalized if it puts mass where reality has none, so the model violently shrinks. It completely ignores one mountain and sharply narrows to lock onto just a single peak to stay safe. We call this mode seeking. Now, what's really interesting here is Section 4, the math and the code. How do we translate that dramatic geometric morphing into raw executable code? Well, the foundational equation for KL divergence is that it equals the cross entropy of P and Q minus the entropy of P. Here's the kicker. The entropy of the true data, H of P, is a baseline constant. We can't change reality, right? Therefore, optimizing cross entropy is the exact mathematical equivalent of minimizing KL divergence. This is exactly why you see cross entropy loss functions everywhere in PyTorch and TensorFlow. Under the hood, they are literally just optimizing KL divergence, making sure your model's codebook perfectly matches reality. But watch out, because implementing this is a total minefield. Here is a rapid-fire checklist of failure modes for you engineers out there. First up, the NaN explosion. If you use PyTorch's f.claw_div API, never ever pass it raw probabilities for your model. Because if your model guesses 0 for an event, the math attempts to divide by 0, and your GPU explodes with NaNs. Always pass the log probabilities. Second is posterior collapse in variational autoencoders. This is where the KL penalty gets way too strong and the model just gives up and outputs noise. And third is mode collapse confusion. That's when you use a reverse KL penalty on data that has multiple valid variations, which wrongly forces the model to only ever generate one single type of output. Let's see how this plays out in the real world. Section 5. Why models get blurry. That mode collapse confusion actually leads us perfectly into seeing how the geometry of KL divergence dictates the absolute success or failure of the most advanced models out there. Let's contrast two absolute titans of AI. Variational autoencoders, or VAEs, are trained using the evidence lower bound, which heavily minimizes reverse KL, so they are mode-seeking. Contrast that with large language models. When they are fine-tuned with reinforcement learning from human feedback via PPO, PPO actually uses forward KL as a mathematical leash. It strictly forbids the model from forgetting English words by heavily penalizing it if it drops probability mass on valid vocabulary. So we have mean-seeking versus mode-seeking. So the crucial takeaway is how this ultimately affects the final product. Ever notice how VAEs tend to generate slightly blurry, washed-out images? It's not a bug, it's the math. Because VAEs use reverse KL, the model is utterly terrified of generating sharp, high-variance pixels that might accidentally fall into a zero-probability valley in the training data. The penalty for that would be infinite. So to stay completely safe, it just outputs averaged, safe pixels. Geometry doesn't lie. If the model is blurry, the math told us it would be. Which leaves us with a really fascinating final thought. If reverse KL forces safe blurry images just to avoid empty spaces, and forward KL stretches models so thin they just average everything out into mush, what happens when we use symmetric divergences? What happens if we use entirely different math, like Jensen-Shannon divergence, which actually penalizes in both directions equally? Well, that is exactly the mathematical breakthrough that gave us generative adversarial networks, or GANs, and their incredibly crisp, photorealistic images. But the math of GANs, well, that is a topic for our next explainer. Keep learning, keep optimizing, and I'll catch you next time.